Guys, good evening. So we are going to discuss the distribution of moments, which is actually an introduction to the limit analysis applicable particularly to beam behavior. So when the inelastic behavior of concrete at a particular location has been accounted for in the design of concrete section, it is somewhat illogical or reasonable to use the results from the elastic analysis in the determination of these moments and shears. So what we are going to do is to put up a procedure, we call it moment redistribution, to make sure that uh, the forces, particularly the bending moments and the shear forces, will actually represent the inelastic behavior of the beam by adjusting the moments based on the nonlinear property of a particular section. So we call that moment redistribution. So we have here a, a graph of the moment curvature relationship uh, representing steel beams or steel sections and reinforced concrete sections. Okay, so for a steel section, the EPP or the uh, elastic perfectly plastic um, behavior is somewhat uh, an ideal representation of the behavior of steel. While for RC, we make use of a similar uh, EPP composed by two lines. One is the elastic, so this is now the elastic behavior, and the other line here is the inelastic or plastic behavior. So normally, plastic uh, behavior in steel design is equivalent to the inelastic behavior in reinforced concrete design. So this characteristic of this moment curvature, uh, which can also be converted into a moment rotation uh, graph, actually is the basis for uh, our actual design moments and shears to be used in our design of the concrete section for a particular location. So this figure now is an ideal relationship that defines the elastic portion and the plastic portion uh, at the two stages of your beam. So take note that in the reinforced concrete design, the lower the net reinforcement ratio, uh, rho minus rho prime, the lower the actual moment rotation behavior is to the ideal. Okay, which means that the basis for our redistribution depends very much on this net uh, reinforcement ratio, where rho is the tensile uh, steel ratio, and your rho prime is the compressive stimulation. So for a simple supported beam, the limit load on such a system is reached when the rotation angle under the load reaches the value of the ultimate rotation. Okay, so take note that in our previous lecture, the ultimate rotation theta is simply equivalent to the ultimate curvature multiplied by the length of the plastic hinge. Okay, so the unit of such rotation is in radians. So this uh, angle theta u, which corresponds to the extreme fiber uh, strain of your concrete, epsilon cu at the point of crushing, uh, assumed or defined rather in the ACI as 0.002. So we have here a figure on the limiting condition for a simply supported beam to undergo what you call a collapse mechanism. So if you have here a force or a load WU, so since the uh, degree of indeterminacy is zero, okay, so the degree of uh, kinematic indeterminacy is equal to zero, then the number of plastic hinges, okay, is simply equivalent to DOI plus 1. Okay, so we have here 0 plus 1 is simply 1. So you need only one plastic hinge formation to make this system collapse. So we call this now a collapse mechanism. Okay, so for static indeterminate fixed end beam, as the load is increased, the moment at the fixed ends achieve MP, while at all other points the moment are still elastic. Okay, so we know that the fixed beam scenario gives you a larger, okay, a bending moment at the supports. That's why we expect, okay, a beam which is ideally prismatic to have reached its yield, okay, its yield capacity first prior to the section at the midspan. Okay, so the plastic hinge formation therefore uh, would be initiated at the ends, but of course if we have uh, to get the ultimate load WU, so the section at the midspan will also develop plastic hinge, and since this is degree of freedom for this particular fixed beam is equal to 2, so the number of your plastic hinge will then be equal to DOI plus 1. So we need, okay, we need at least 3 plastic hinges or plastic hinge to form prior to the total collapse of the system. So we need plastic hinge at the two ends and one at the midspan. So for this particular scenario, we can actually derive, no, the yield uh, load WY by simply, okay, equating your plastic uh, moment with that of the maximum uh, elastic. Okay, elastic value WL squared over 12. So if we transpose this of expression, so we can determine WY based on the value of your MP, so 12 MP over L squared. So take note that at this point the beam behaves as a simple beam but deflects less because of the end moments MP. Okay, so we're still on the boundary of the elastic limit, which is the yield point. So the limit load may also be computed as that which is equivalent to a simply supported midspan moment of WL squared over 8 if we are going to consume all or expose all the plastic moments at the two ends of the beam and at the midspan. So we have here what you call a plastic hinges. So at here, here and here. So at a certain point, upon increasing the load WU, all this section will reach its uh, maximum capacity MP. And for ease in computation, we assume that this beam is prismatic, hence your plastic capacity MP will all be the same uh, of the same value. Then equating it to the static moment, because we know that this is just equivalent to the static moment here, which is simply 2 MP. Okay, so the average of these two moments here is still MP, so MP plus MP is 2 MP. Then uh, 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 equating this to the simply supported moment of WL squared over 8, we can now get the value of WU, which is simply 16 MP over L squared. Okay, so take note that the ultimate load is actually uh, greater than the yield load at the uh, boundary, the upper boundary of the elastic limit. So if we divide 16 by 12, we can say that there is a multiplier equivalent to 4 thirds. Okay, so this 4 thirds is actually an excess capacity that you can get out of uh, the plastic hinge formation that was exposed, no, from the two ends of the beam and the midspan. Okay, so the capacity now is actually increased by 33%. This is equivalent to 133%. So 33% after the plastic movement has been reached at the fixed end, provided that the sufficient additional deformation or rotation can be accommodated at the fixed end to permit the development of the plastic moment at the midspan. In short, MP undergo any particular loading condition are realized at both positive and negative moments. So when we're talking of this increase in capacity, we have to see to it that uh, the plastic hinge must, okay, develop such a ductile uh, behavior, and this uh, development of this ductile behavior depend much on detailing practices. Okay, so we have to see to it that all the details, especially on reinforced concrete members or sections, must be properly taken care of. So that's it for the first part of the redistribution of moments. So I'll see you on the next video to explain to you the process on how to do uh, the procedure on moment redistribution. Thank you very much for listening. I'll see you in the next video.